Hello everyone, welcome to today's first session of ACT. Our first talk is going to be by Lachlah McPheat. And before we start with the talk, I should remind you about the protocol for questions. So if you have any questions, please either put them in the Zoom chat or raise your hand and then I'll call on you. We'll have 5 minutes for questions after the end of the talk. So now, Lachlah, please go ahead.
Thank you. I'm just going to share a presentation so you can all see. So it'll be me and also Hadi presenting categorical vector space semantics for Lambek calculus with a relevant modality. And this is joint work together with myself and Mehrnoosh Sadrzadeh at University College London, Hadi Wazni from Queen Mary University of London, and Gijs Wijnholds from Utrecht University in the Netherlands. And before starting the whole presentation, I want to thank the organizers for running this conference so smoothly in spite of a pandemic. And I also want to thank last year's organizers, or maybe more specifically for Adjoint School, because this project is an offshoot of a project from last year's Adjoint School. So now, to start deciphering this rather intimidating title, I want to show you what you can do with the categorical vector space semantics for Lambek calculus with a relevant modality. The goal is by the end of the talk, to be able to talk about the following phrase as a linear map, or the meaning of this phrase as a linear map. And the phrase is the papers that John signed without reading. And what's happening here is a bit tricky linguistically. There's something known as parasitic gapping going on, and I'll take a second to explain what that means. A parasitic gap is a gap that depends on another gap. So it'll help to know what a gap is. And a gap here, or we have two gaps in this phrase, one after the word signed and one after the word reading. And all you need to think of a gap is that this first gap refers to the word papers. See, these are the things that are being signed. And the second gap refers to the words, well, this gap after what's being signed. And because the second gap refers to another gap, we call the second gap parasitic, right? And this is all the linguistics we need to know. Parasitic gaps exist, and they're kind of hard to pass in a computational setting. But we're going to try and do it. And how are we going to do that? Well, this is the outline of attack. First, I'll introduce to you compositional models of grammar, where I'll define bang L star, the Lambek calculus with a relevant modality. Then I'll sort of complementarily describe what distributional semantics are and how we use them. And then I'll introduce DiscoCat, distributional compositional categorical semantics, as a method to fuse these two models. From there, we'll start defining our categorical semantics for bang L star. And I'll introduce a diagrammatic calculus for this logic or this semantics so that we can prove soundness in a nice way. And then from there, I'll define vector space semantics of bang L star in terms of nice functors from the categorical semantics into FDVect. Then I'll hand over to Hadi and he'll explain how we actually test these models on data to see if we can actually do what we want to do. So let's start with compositional models of grammar. And just a word of warning, there's lots of models you could choose. We work with the Lambek calculus. And to define a Lambek calculus, initially you define some set of atomic types denoted at. From this, you generate all types of the calculus. And the way you want to read this is that a type phi of the Lambek calculus is either empty, it can be atomic, it can be a concatenation of two types, or a forwards fraction of two types, or a backwards fraction of two types. And as the talk evolves, this notion of fraction will become clearer and clearer. Once we know the types, we can define the sequence, and these are written in this form: gamma derives A, where a capital Greek letter on the left-hand side always stands for an ordered set of types. And I like to think of these as a concatenation of types, because I don't like the notion of a set on one side and type on another, but if you're fine with that, it's an ordered set. So now we know the types, we know the sequence, now we have to look at the rules of the calculus, and our Lambek calculus has 5 rules. One of them is this axiom that says from nothing we may deduce that any type derives itself. And then in general, for a presentation, you'll have a left and a right rule for every connective. We don't have one for concatenation for simplicity's sake, but we do have them for the slashes, for the fractional connectives. So for the backslash, we have the left rule that says that from gamma you can derive, if from gamma you can derive A, and if from delta 1 B, delta 2 you can derive C, then from delta 1 gamma A under B delta 2 you can derive C. And for the right rule, we have if A followed by gamma derives B, then gamma derives A under B. And this might sound like sort of syntactic word soup. It definitely did to me when I started this project. But in the categorical semantics, this becomes a lot clearer to understand. I'll show you what the right rule looks like later. But so now we know what the Lambek calculus is. And I want to show you how we use this to model grammar in natural language. So we start today just with English grammar. You can do this for plenty of other languages too, though. And we set our atomic types to be N and P and S, where N stands for noun, like banana, and P stands for noun phrase, like green banana, and S is a sentence, like green bananas ripen. And then we have the more complex types, for example, MP over N, or MP over MP, and these are the types of adjectives. And then we have verb types. So for example, there's intransitive verbs, NP under S, and transitive verbs, NP under S over NP. And I just want to give you some more intuition around these types. We want to think of adjectives, for example, as functional. That's where this fractional idea comes in. Because if you multiplied NP over N by N on the right, this should reduce to NP somehow, right? So an adjective you apply to a noun to produce a noun phrase. This is a sort of notion that we're trying to mirror with these types. And we actually see this when we start talking about sequence in this setting. A derivable sequence in this setting is a grammatical reduction. So for example, green bananas, we know this is a noun phrase, but we also know that bananas is a noun, and we know that green is an adjective. And so we can form the sequence NP over N followed by N deriving NP, and we can prove that it's, we can find a proof for it, i.e. we can show that it's derivable. And so we know that in Lambek calculus, we can prove that green bananas is indeed a noun phrase. And this moves grammar from a human exercise to a formal one, which is super nice. And in the same logic, you can show that bananas green doesn't reduce to anything sensible. So this is already quite a nice model of grammar, but what about the phrase that we started with, the papers that John signed without reading? In just Lambek calculus with conventional typings, this doesn't pass. So to try and find a setting where this phrase does pass, we move to an extension of Lambek calculus. And this is the extension with a relevant modality as defined by Karnovich, Kuznetsov, and Skedrov in the paper about the undecidability of this calculus. And to define this for you, it's pretty similar. We have almost all the same types as previously, but now we also have these types. And I'm going to be reading this as bang. So these will be the banged types or the modal types. And obviously, when you introduce a new connective, you introduce new rules for the calculus. So we have a bang left rule, a bang right rule, and the permutation 1, 2, and contraction rules. So bang left and right tell you how to introduce the bang, permutation 1 and 2, and contraction tell you how to play with it. And they are probably the most important rules. So I'll show them to you now. Permutation 1 says that bang types on the left of a sequence can be moved to the right of an adjacent type. Similarly, permutation 2 says that bang types can be moved to the left of adjacent types. And contraction says that if we repeat a bang type in the left of a sequence, we can contract them to a single instance, right? And with this new system, with this new logic, we can actually pass the phrase papers that John signed without reading. And it looks like this, which is kind of intimidating. Well, I think it looks intimidating and I work with this. But if I can pull your attention to the papers that John signed without reading, that each word in this phrase are given the following types here. So the root of this tree is exactly the sequence that says that this phrase parses into a noun phrase. And this tree tells you how. And that's what we want. This is a syntactic model of parasitic gaps. But there's limits of these models as well. It's slightly different to the last limits I was talking about. And this is that these models are purely syntactic. They don't have so much semantic information. So for example, consider dogs chase cats and cats chase dogs as two sentences. Lambek calculus can tell us that these are both sentences, but it doesn't tell us so much about the difference of the meaning of these two sentences. And as English speakers, we know that there's a difference in the meaning. So we turn to distributional semantics as a source of meaning, or as a model of meaning that we want to fuse into here. And distributional semantics are given this name because of the distributional hypothesis, which, I mean, probably most famously is coined by Harris and Firth. And you can say it in so many ways, I'm going to describe it as words used in similar contexts have similar meanings. And informally, this has been described as the Yone dilemma of natural language, which I quite like, but I'm not going to extrapolate on that any further. But it's a fun thing to say in this conference, right? And just to outline how these models work, broadly speaking, distributional models read large bodies of text, like think Wikipedia in British English. And a distributional model will read this text and produce a word embedding for each word in the text. And this is just a nomenclature. A word embedding is just a vector containing this distributional data of the text. And the thing is that word embeddings actually verify the distributional hypothesis. They actually act in the way that the hypothesis assumes. So for example, there's this fun proof of this where word embeddings actually accurately answer TOEFL questions about word similarity. And they do it pretty well as well. So word embeddings actually do what the distributional hypothesis suggests. And they're actually useful, is what I want to go to next, in what we'd call downstream NLP tasks, natural language processing tasks. So for example, automatic essay marking uses word embeddings. Thesaurus extraction uses word embeddings. Machine translation uses word embeddings. So there's a lot of machinery that depends on distributional models. But these models also have a problem, and that's that they are not they're not grammatically compositional. You can compose the vectors in these models in some way, but usually it doesn't make sense in a grammatical setting, which is, yeah. And so we turn to distributional compositional semantics as a way to fuse the distributional semantics and the compositional grammar that I've introduced so far. And a very famous model of this is, of course, DiscoCat, distributional compositional categorical semantics, which makes distributional models grammatically compositional. And you could actually reword this as DiscoCat is categorical vector space semantics for Lambek calculus, or it's equivalent to this. And what we've done, obviously, the title of the paper, we provided a categorical vector space semantics for bang L star. So I'll now take you through how we build this categorical vector space semantics. And we do this in a two-step process. So first we define a categorical semantics, which I'll do on this slide. And then we define a vector space semantics or several vector space semantics in terms of functors from the categorical semantics into FDVect. And the categorical semantics is quite nice and easy to define. You interpret the types of Lambek calculus as objects of a monoidal biclosed category called C of bang L star, and it has these two additional structures of restricted symmetry and Coalgebra modality, and the Coalgebra modality is denoted by bang, just like in the logic. And I'll explain what these are later, but just so we have a grasp of what the objects are, we'll interpret the empty type as a monoidal unit. We'll interpret atomic types as distinct objects of this category. I might refer to them as atomic objects. We interpret concatenations of types as the monoidal products of their interpretations, and we interpret the fractional types as internal HOMs from the interpretation of the denominator to the numerator, which is horrible to say with words, but very easy to see algebraically on the page. And then we want to interpret the modal types. And this kind of looks like a cop-out. The interpretation of a modal type is bang of its interpretation, but this bang here on the right-hand side is a Coalgebra modality, which I'll define properly on the next slide. But before I do that, I want to show you the morphisms of this category. So we interpret the derivable sequence of bang L star as morphisms of C of bang L star. That is to say that if we have a sequent from gamma to A, or you can derive A from gamma, then there is a morphism from the interpretation of gamma to the interpretation of A. That's what we say. So what is this Coalgebra modality? It's kind of crucial. A Coalgebra modality on a monoidal category is a lax monoidal comonad, which we'll call bang, on that category, such that for any object in the category, once you apply bang, that object receives a comonoidal structure. And this is defined in Blue, Cockett, and Seeley's papers on differential categories. And it's quite neatly defined there if you want to see more details. But I just want to draw your attention to the most important structure for this talk, at least, which is that once you apply bang, you can co-multiply the things you've applied bang to. Because I know there's a lot of structures floating about. This is by far the most important one for today's talk. And this concludes the definition of our categorical semantics. We know where the objects are, we know where the morphisms are. Or you could say, we know where the types are sent and we know where the derivations are sent. or the sequence ascent. But now we want to show that this categorical semantics is sound, i.e. we want to show that any proof in the logic also holds in the semantics, right? But to do this, I just want to show you, set up a diagrammatic semantics so I can show you the proof of soundness kind of neatly. And we have a pretty standard setup where we interpret objects as labeled strings and morphisms as boxes on strings, reading from top to bottom. And as usual, it's a monoidal category, so we have juxtaposition, horizontal juxtaposition as monoidal products. And then we refer to the bias and stay clasp diagrams to denote the internal homs. So here are the rightwards facing ones denoted by this clasp. And also, obviously, because it's monoidal by closed, we have caps and cups corresponding to currying and evaluation. And these diagrams are the left ones. You also have right ones, but I don't want to clutter the page too much. So this is all standard setup. What's new for us are the Coalgebra Modality diagrams. So we've chosen to denote modal objects by fixed strings rather than thin strings labeled with modal with a modality. And what's important with fixed strings is that you can split them. So this is the co-multiplication that I was talking about before. And for the keen listeners, you maybe picked up that I didn't define the restricted symmetry, and we can draw it quite nicely grammatically here. And the restricted symmetry just says that we can cross thick strings with thin strings. And I've drawn one diagram here, you can cross them the other way as well. It's a natural isomorphism between bang, the comonad, or the Coalgebra modality, and the identity functor on the categorical semantics. Ooh, sorry. There we go. Right, so now, whoa, this has jumped a bit. So I'm now going to prove the soundness of these semantics with respect to our logic. And you can see on the slide it's sufficient to show that all the rules of the logic also hold in the semantics to show that we have a sound interpretation, right? And so here on the slide, you can see probably the easiest rule to interpret, and that's the axiom, which says from nothing we can derive that any type proves itself or derives itself. Categorically, this means that from any object, there should be a morphism from that object to itself. And because we're in a category, we have that. Diagrammatically, it's also quite easy to see this interpretation. We'll draw this string. We don't draw identity boxes as usual. And then maybe for a slightly more exotic rule, the \right rule in Bang star, it says that if A followed by gamma derives B, then we know that gamma derives A under B. Categorically, this says that if there's a morphism from A times gamma to B, we should be able to create some morphism F bar from gamma to the internal homs A to B. And I mean, hopefully some of you see where this is going. Diagrammatically, this says that if we have a morphism like this one here on the left, with these two incoming wires, we should be able to bend one of the wires to create this morphism on the right? So this is all very standard setup. So I just want to show you what this looks like, or how one of the rules that are not part of a standard setup. So for example, a contraction rule, which remember logically says that if we repeat a bang type on the left of a sequence, we may contract it into a single instance of that type. Categorically, that says if we have this morphism F from delta 1 times bang A times delta 2 to C, we should be able to create a contracted morphism from delta 1 times bang A times delta 2 to C, which is, again, quite wordy, but diagrammatically it's quite easy. It says if we're given a morphism like this, which I've drawn quite suggestively, we should be able to create a morphism that goes from a single instance of A and delta 1, delta 2 to C. And that's quite easy to do in this setting. We can just split the fixed string A in the middle and then apply F. Let's draw a box around this and call it FC. And algebraically or equationally, you can define it as such. FC is F applied to identity on the outside, splitting in the middle, identity on the right side. So I'm going to conclude this sketch proof of soundness here, but hopefully it's illuminated how we do it, and maybe the rest of the paper will be, or the rest of the proof will be quite easy to read now. But instead I want to start moving towards the vector space semantics, the real meat. So like I said before, we want to define vector space semantics in terms of structure preserving functors from our categorical semantics into FD-vect. And when I say structure preserving, I mean on the nose, every single structure should be preserved. So that means that monoidal units should be mapped to monoidal units. Atomic objects will be mapped to atomic vector spaces, vector spaces. indexed by the atomic types. Monoidal products will be mapped to tensor products, and internal HOMs will be mapped to internal HOMs, as you expect. But then we get to this frustrating interpretation of modal objects, because as far as I know, there's no obvious coalgebra modality on FDVect. So where do we send modal objects? So yeah, in order to make any sort of sense of this, we start defining coalgebra modalities on FDVect to make a sensible definition of such a functor. And we have a few candidates. So the first one has more theoretical implications. We'll refer to it as duals of tensor algebras. So remember, a tensor algebra of a vector space or a Fock space of a vector space is this construction. So T of V is this huge sum. And on here you have just a standard multiplication given by concatenation of simple tensors. And you can dualize this in the vector space sense. So we'll use this bottom symbol for vector space dual. And dualizing this gives you a co-multiplication. And like I said before, this is what we're looking for. We really want co-multiplications, right? And also noting that T is a free functor from vector spaces to algebras. Here I mean associative algebras. We know that there's an adjunction then. So a free forgetful adjunction, which then defines a monad on vector spaces. And we're looking for a comonad, and we can get one by dualizing, according to the Brigier and Verlaisier-Hopf-monads paper, which is super nice. So we have a comonad on vect, and on things that you apply the comonad to, you have co-multiplication. So we have all the setup that we want, but obviously T of V is infinite dimensional for any sort of interesting vector space. So we have to restrict ourselves. And we do this by, instead of using T, we apply a fermionic Fock space functor or antisymmetric algebra functor, or if you like Lie algebras, the Grassmannian algebra functor, known like this, defined almost identically, but we replace the tensor product with the antisymmetric tensor product. And this, on this space, there's also a multiplication, although it's antisymmetric, but that's totally fine. This functor is also free, so there's another monadic structure, this time on FDVect. So we have a pretty similar setup to the last slide, but and then dualizing gives us the same comonad and the same, oh, not the same obviously, but it also gives us a comonad, and it also gives us a co-multiplication from f of v to f of v tensor f of v. And I don't draw any vector space duals here because up to isomorphism in this setting, this is exactly the typing of the map that we have. But there's problems with this model, with this coalgebra modality, because of computational constraints. So simply said, if V is n-dimensional, then f of v is 2 to the n-dimensional, making the co-multiplication matrix 2 to the n by 2 to the n squared, which is not tractable for us to work with right now because our n is in the hundreds. So it is practically very hard to work with, but it still has theoretical implications in spite of these difficulties. And I reference here the Panangaden and Seeley-Blute paper, where they use Fock spaces as a model of full linear logic. So the Fock spaces here will be the interpretation of the exponential modality of linear logic. And they make great use of it there. So we suspect that there are offshoots of this that we could use in practice too. But for now, we have only really been able to work with the identity comonad on data. And so to define coalgebra modalities on the identity comonad, remember that is defining a comonoidal structure on vector spaces in this case. And most importantly, like I said before, this boils down to defining a co-multiplication from a vector space V to V tensor V. So we have two candidates of coalgebra modalities. So for a vector space V with basis V1 through Vn, the first coalgebra modality we define, we'll call the co-free inspired one. So we have co-free inspired co-multiplication defined on a vector V, which maps a vector V to V tensor 1 plus 1 tensor V, where 1 in this case is a vector full of ones, the sum of basis vectors. And this is very similar to the co-free coalgebra on a vector space, but not identical. So we say inspired, right? And then the other model that we defined is called the Coalgebra co-multiplication, which you define on a basis and extend linearly by just copying the basis. And you can almost define these two maps as, well, you can almost say that these two maps below are the same. Please ask me about the almost later if it's not obvious. And we call these Coalgebra A and B. So you map, Coalgebra A maps a vector V to V tensor 1, and Coalgebra B maps V to 1 tensor V. So here, these bullet points 1 and 2 are exactly defining Coalgebra modalities on the identity comonad. And with these, it's actually enough to start testing this on data. But before doing this, and for reasons that are perhaps not obvious given the motivation I've given you, we want these co-multiplications to look as much as copying as possible. And by copying, I mean this. We call it a full model. It's clearly nonlinear, but like I said, this is what we're trying to model or approximate with linear maps. So I'm ready now to hand off to Hadi to explain how we actually test these models on data. So I'll do that now.
Okay, to check the correct semantic representations, we implemented the resulting vector representation on a large corpus of data, and we experimented with a verb disambiguation task. Basically, this task contains phrases with verbs with two possible interpretations. For example, private company file annual account. File is the ambiguity verb. It could mean register as a private company register annual account, or private company smooth annual account. To do so, we extended a previous data set with a second verb and a proposition. We changed a pair of transitive sentences to a set of pair of parasitic gap phrases. For example, accounts of the local government filed, we changed it into accounts of the local government filed after inspecting. So we added a second verb, which is inspecting, was chosen from a list of verbs that most frequently appeared with the verb of the original sentence. Also, we added a preposition, which was chosen from phrases having the first verb or decided based on the meaning of the second verb. We annotated the entry of the data into binary, where 0 indicated a bad disambiguation pair and 1 a good one. So for example, this entry will lead us to 3 phrases: annual account of private company file without approving. The other one is register without approving. And the third one is smooth without approving. To experiment with this, we built vectors for the phrases P, P1, and P2. And we checked whether the vector of P is closer to the vector of P1 or vector of P2 using cosine similarity. And we computed the mean average precision by counting in how many of the pair vectors of the phrase with the ambiguous verb in it is closer to the vector of the phrase with its appropriate meaning. For this setup, we experimented with 3 neural embedding architectures: BERT, fast text, and word-to-vec continuous back of words. We used a pre-trained model called BERT based on case, where we extracted the embeddings from the internal hidden layer of the network. For word-to-vec and fast text, we trained with a minimum word frequency of 50 and a window of 5 over 15 iterations using the UK Wikipedia corpus. Also, the phrase embeddings obtained by adding word embeddings. In addition, we created the verb for each verb, a verb matrix. We collected a large set of sentences from UK WIC corpus. We built for each verb, as I said, the matrix by summing over the canonical product of the respective subject and object vectors of the verb. And the results are shown in this table. These results, unsurprisingly, the best disambiguation result was obtained via the BERT phrase vectors, having a map of 0.65. This is not surprising. This is unsurprisingly because BERT is the state-of-the-art contextual neural network, and it provides different meanings for words in different contexts, and it's trained on a large data set. However, as you can see, the full and the co-free inspired approximations provided better results in case of the fast text and the word-to-vec. And in the fast text co-free inspired, we got a 0.56, and the full model 0.57, both better than the fast text, which is 0.55. as well as for the full and the co-free inspired showed similar results, 0.54 better than the word-to-vec, which is 0.46. In the 3 experiments, the Coalgebra A did better than the Coalgebra B. And we can say that the co-free inspired also in the 3 experiments followed the full model. So to conclude, we have provided sound categorical and vector space semantics for the Lambek calculus with the relevant modality. We provided different vector space interpretations for the relevant modality and experimented with the disambiguation task. We extended a data set, previous data set, to a parasitic gap phrases. We implemented the model using 3 different neural networks. One of our interpretations performed very similar to, and in one case, the same as a full but nonlinear copying model. The best categorical phrase model performed better than the additive neural phrase embeddings. For sure, the results can be improved by building better quality verb matrices, which is a task we are working on right now. For a future work, we aim to explore bounded bank syntaxes, improve the current models with more training and different architectures, applying bang L star to other linguistic phenomena such as coreference, and prove coherence of diagrammatic semantics. So this ends the talk. Thanks.
Thank you. Okay, so we've had a number of questions in the chat, and I think many of them were actually answered in the chat already. So if anyone posted a question to chat and you feel it hasn't been answered yet, maybe you can raise your hand and ask it again now, so we can kind of get a more thorough answer than. Alex.
Hi, my question is about the bang modality. So I guess this is for the first speaker. I thought to have a good interpretation of bang, that the image of morphisms under the modality should be natural with respect to the copier, which it doesn't look like that's the case for the identity comonad.
Yeah.
So.
It's not, and like in the definition given the differential categories paper, it's also not natural, but I, like you, assumed it would be. And then I went on to define all these Coalgebra modalities, and then I realized once when I started experimenting with them that, like, oh no, nothing is a comonoid morphism. Have I just not understood it? And then I reread the definition, and yeah, there's no need for it, at least within differential categories, which is where we draw the inspiration from. But I'm also surprised that this definition is so useful.
Okay, yeah, that's also a surprise to me. Thanks.
No worries.
Could I ask a question?
Go ahead.
Thank you for the talk. So I was wondering about the use of the fermionic box space or exterior algebra. So you get this anti-commutativity property, which seems to suggest that sort of word lists, if you change the order of them, will negate. Is that semantically all right? Is that or is that justified in any way, or does it just work?
Well, I would say the short answer is it just works. But what you want to remember is that we don't actually use the multiplication. We use co-multiplication. So what you see happening is that you apply co-multiplication to a simple tensor, and what you get is all possible products that would multiply to get that tensor. And yeah, I still don't have a good way to think of what's going on in the semantics, but I can definitely say that it's not as simple as a single word pair switching the order and their meaning being negated, because remember, these vectors in these spaces are, you could say that they're a lot more than the vectors in the non-fermionic box spaces. if that makes sense. So it's not as one-to-one as you'd hope.
Thank you.
Okay, there were another couple of questions earlier which I think haven't been answered yet. So Giovanni asked whether BERT gives subject and object vectors for each verb, and Martha asked whether whether you take the BERT sentence embeddings or word embeddings. So I guess this is a question for Hadi.
Yeah, for the data set, we extracted in each sentence the subject alone, the object alone, and we got the vectors using BERT. Do you take BERT sentence embeddings or word embeddings? We experimented both the word embeddings for the BERT, and we experimented the phrasal embeddings also.
Thank you. Are there any other questions?
I guess I have a question.
Go ahead.
Lachlan, so you said the exterior algebra or Fock space thing had kind of different, you thought of it differently than you thought of the ordinary vector space. Do you still have things like king, like the individual pure tensor king and queen and stuff like that? And is it still true that this fun thing about king minus queen equals man minus woman, can you still expect that sort of interpretation?
So the short answer here is that I don't know how to interpret them, because there has to then be some sort of, well, yeah, what we'd need for this to make sense in my mind is some sort of unit from the normal space where king and queen and whatnot would live into the space. And you can have this, I mean, you have this natural embedding into the first layer of a Fock space. Well, I say natural quite flippantly now, I'm not, don't hold me to it. So you could mirror that behavior just quite trivially like that. But if you had this sort of an amplified king vector where you have, king in each layer of this Fock space, I wouldn't be able to tell you off the top of my head if you'd expect the same, if you could see the same behavior.
Right.
It's something we haven't played
right,
with.
but yeah, you're right. The lower, the degree 1 stuff is just the same as the underlying vector space. So I guess if you just had the pure king, you could still, still subtract pure queen.
This is one of the reasons I want to look at bounded syntaxes or bounded bang syntaxes, because then we could actually cut off this tensor space or this tensor construction after a certain layer bounded by some natural number. And then hopefully we could practically reason and test vectors that would live in this bigger space, but not infinite dimensional one, or at least not very big one, as in the fermionic case.
Thanks.
Can I add something to this? So I'm wondering why you chose the fermionic Fock space as opposed to the bosonic one. Because I think that for a finite dimensional vector space, the fermionic Fock space is finite dimensional. It's kind of like the power set of the base, like the basis elements of the fermionic Fock space or the power set of the basis of the underlying vector space. So it's finite dimensional. And then, so you cannot have twice the same state inside. So you can't have V1 tensor V1 because that's 0 by antisymmetry. So I'm wondering why you chose that one and not the bosonic Fock space, which is more like a multiset where you can keep adding things.
So it was specifically for the reason to restrict, so we could end up with finite dimensional spaces. That's why we chose fermionic, because bosonic is not, it does not produce finite dimensional spaces. But it is also, it's also studied in that paper that's referenced, the Panangaran, Bluton, Seeley paper, where they use Fock spaces to model exponential modalities. They consider all those options. So people do, but to end up with infinite dimensional spaces, you can't.
Okay, thank you. I think this is probably the end of our question time. So please let's thank the speakers again via clap emoji or in the chat.